title of the module is Minimum Spanning Tree Algorithms. In this session, we will discuss the Prim's algorithm, Boruca's algorithm for minimum spanning tree briefly. First, let us see the definition of the spanning tree. A spanning subgraph H of a connected graph G such that H is a tree is called a spanning tree of G. Once again, let us recall the weighted graph. The weighted graph is, let G be a connected graph, each of whose edges is assigned a number called the cost or weight of the edge. We denote the weight of an edge E of G by W of E. Recall that such a graph is called a weighted graph. Now, let us see the definition of a minimum spanning tree. A spanning tree of G whose weight is minimum among all spanning trees of G. Such a spanning tree is called a minimum spanning tree, also denoted as MST. Let us see some results based on the MST theorem. If all edge weights in a connected graph G are distinct, then G has a unique minimum spanning tree. Proof: let G be an arbitrary connected graph with two minimum spanning trees T and T dash. We need to prove that some pair of edges in G have the same weight. The proof is essentially a greedy exchange argument. Each of our spanning trees must contain an edge that the other tree omits. Let E be the minimum weight edge in T difference T dash, and let E dash be a minimum weighted edge in T dash restricted to T, breaking ties arbitrarily. Without laws of generality, let's suppose that W of E is less than or equal to W of E dash. The subgraph T dash union E contains exactly one cycle C which passes through the edge E. Let E double dash be any edge of the cycle that is not in T. At least one such edge must exist because T is a tree. We may or may not have E double dash is equal to E dash. Because E belongs to T, we immediately have E double dash not equal to E, and therefore E double dash belongs to T dash restricted to T. It follows that W of E double dash is greater than or equal to W of E dash, which is greater than or equal to W of E. Now consider the spanning tree T double dash, which is equal to T dash plus E minus E double dash. This new tree T double dash might be equal to T. We immediately have W of T double dash is equal to W of T dash plus W of E minus W of E double dash, which is less than or equal to W of T dash. But T dash is a minimum spanning tree, so we must have W of T double dash is equal to W of T dash. In other words, T double dash is also a minimum spanning tree. We conclude that W of E is equal to W of E double dash, which completes the proof. The problem of finding a minimum spanning tree in a connected weighted graph is called the minimum spanning tree problem. The importance of the minimum spanning tree problem is due to its applications in the design of computer, communications and transportation networks. The history of this problem was researched by Ronald L. Graham and Pavel Hell in 1985. They concluded that the minimum spanning tree problem was initially formulated by Otakar in 1926 because of his interest in the most economical layout of a power line network. He also gave the first solution of the problem. Prior to, however, the anthropologist Jan Sanowski's work on classification schemes led him to consider ideas closely related to the minimum spanning tree problem. Over the years, this problem has been solved in a variety of ways using a number of algorithms. One of the best known was discovered by Joseph Bernard Kruskal, 1928 to 2010. Another well-known algorithm for finding a minimum spanning tree in a connected weighted graph was developed by Robert Clay Prim, born in 1921. Like Kruskal, he received his PhD from Princeton in 1949. He was the Vice President of Research at the Sandia Corporation. The paper containing the algorithm that bears his name was published in 1957. This algorithm was originally discovered by the Czech mathematician Vojtěch in 1930, but the algorithm is named for Prim. Let us now see about Prim's algorithm. For a connected weighted graph G, a spanning tree T of G is constructed as follows. For an arbitrary vertex U for G, an edge of minimum weight incident with U is selected as the first edge E1 of T. For subsequent edges E2, E3 and so on up to En-1, we select an edge of minimum weight among those edges having exactly one of its vertices incident with an edge already selected. The figure shown on the screen illustrates how to construct a spanning tree of a connected weighted graph by Prim's algorithm. Again, a tree obtained by Prim's algorithm is also a minimum spanning tree, as we shall be seeing later. The next theorem is Prim's algorithm produces a minimum spanning tree in a connected weighted graph. The Prim's algorithm is: let G be a graph on n vertices. Select arbitrarily any vertex. Call it V1. Choose the edge of minimum weight among the edges incident at V1. Call the other end of this edge as V2. Consider the tree V1, V2 as a subgraph of G. Choose the edge of minimum weight among the edges incident on V1 and V2 and such that the order of the end vertex V3 of this edge is in G minus V1, V2. Consider the tree V1, V2, V3 as a subgraph of G. Choose the edge of minimum weight among the edges incident on V1, V2 and V3 such that the other end vertex V4 of this edge is in G minus V1, V2, V3. Proceeding like this, we get a tree V1, V2, V3 and so on up to Vn. This tree is clearly a spanning tree of a minimum weight of the graph G and so is an optimal tree of G. We shall now see the Prim's algorithm to calculate the minimum spanning tree of a graph. You can see a graph on this board here. I am going to lead you step by step as to how the Prim's algorithm works in order to arrive at a minimum spanning tree. Now here I have these vertices and these are all weights of the graphs. So there are A, B, C, D, E, F, G and corresponding to every edge there is a weight assigned to all the edges. So it is a weighted graph. And in this weighted graph, I am going to find a spanning tree such that the combined weights of the graph of the minimum spanning tree that we will be finding is minimum. So that is the main point of this exercise. And so let us now start. We have A, the vertex A is here. I am going to choose the vertex A. So I am putting S to be, in step 1 I take A inside the set S. And then after V minus S, so the difference V difference S is now B, C, D, E, F and G. So remaining vertices, all the remaining vertices are here. And now the edge set A is empty. So A is the edge set and here it is empty and LE, that is the least weight, the edges of least weight is said to be AB. Why is that? Because here you can look at A, I have chosen A. And with A there are two edges impinging on it, namely this edge and this edge. So among these two edges, the edge with the least weight is this edge AB. Therefore, I am choosing this edge and I am putting it inside my LE. So that is the set. So AB goes there and I am choosing A and I am also choosing this edge. So that is done. Now step 2. Now S has got two vertices now, A and B. So once this edge is chosen, B is also gone. Now I am left with A and B inside S and V difference S has got the remaining vertices, namely C, D, E, F and G, and the edge set has now is now containing one edge alone, so namely AB. AB is the edge that is inside A and the edges among now the least possible weights are BD and AC. How is that? Now I have this vertex B. You can see that there are 3 edges impinging upon B, namely this edge with weight 10, this edge with weight 8 and this edge with weight 9. Among these 3 edges, I can very clearly say that 8 is the edge with the least weight. Therefore, I am choosing this edge and namely this vertex. So, I choose D and also this edge. So, you can put that inside the next set. So, A, B, D are done. A, B and D are done, and the remaining vertices are C, E, F and G as I have shown in this line, and then finally and A, the edge set has got AB and BD. So, that also has been put here. Now, among these edges I have the option of choosing the next possible minimum weight edge. So, I can either start at B or at D or at A, but let me go with D, because from B to E the edge has got 10, from B to C the edge has got 9 and from A to C the edge is 8. So, from here I am seeing that among these, if I go with D, the least possible weight is 2 only. So, the remaining all the other edges are much bigger than 2, and therefore, I am going to go with this edge and I am choosing the vertex C as well as this edge. So, let me put that edge and that vertex here. So, in step 4, I have covered A, B, D and C as shown here. I put A, B, D and C. The remaining vertices are E, F and G. So, that is also written here, and then I have the edges A, B, B, D and C, D. So, these 3 edges have gone into this set, edge set, and now looking here, I look upon all the possible combinations. So, from A I have remaining possible combinations. So, from B I can go to E, or from D I can go to E, or from D I can go to F, or from C I can go to F. So, I can start with any of the vertices that are already chosen and try to find an edge that is of the least weight. So, among these I have 10, 7, 9 and 1. So, the obvious choice is 1, and therefore, I am choosing F and I am choosing this edge. So, I have put that in step 5. Now, the vertex F is also gone, and therefore, you have A, B, C, D and F that is written here. The remaining vertices are only E and G, which have not been covered by the algorithms yet. So, those vertices are in V minus S, and the edges are AB, BD, CD and CF. As you can see, AB, BD, CD and CF, all that has been written here. And now from here I have the option of going from B or D or F in order to grow the tree. The main purpose of Prim's algorithm is that you grow the tree by choosing those edges of minimum weight. And among these possibilities, so there is 10 here if I go from B, there is 7 here if I go from D, and there is also this possibility, but this is already chosen, therefore we should not look at this. But from F, if you look here, there is an edge of weight 2, and that seems to be the most optimum choice because it is the least, and therefore I am going to go with this vertex and this edge, as you can see here. So, this has been chosen and I am putting that here. So, the next edge to be chosen is FG, and in step 6 we are done with A, B, C, D, F and G, as you can see here, and the remaining vertex is only E, which is standing here, and then all the edges that we have already chosen have been highlighted in A. And now the possibilities are I can go from F to E or from G to E, but among these the only way that I can do this is this is the least way. This is the least possible weight. Out of 5 and 6, obviously 5 is least, and therefore instead of going from G to E, I can go from F to E. B to E is again a very wrong choice because the weight is 10. So, you cannot go from B to E in order to grow the tree. Therefore, from F to E I am going. So, now I have chosen E, I am choosing this edge, and that is how we come to step 7. All the vertices have been covered, A, B, D, C, F, G, E. The remaining vertices are none, empty set, and then the edge set is AB, BD, CD, CF, FG and FE. As you can see, AB, BD, CD, CF, FG and FE. Clearly this is a tree. If you want, you can simply draw like this. So this is how the tree looks like. This is A, this is B, this is D, C, F, E and G. So there are no cycles, it is an acyclic graph, and this is the minimum spanning tree that we have arrived from this graph. This is how you do the Prim's algorithm to find the minimum spanning tree. Prim's algorithm is more efficient than Kruskal's algorithm, for we need not check connectivity and cyclicity of the construction at any stage. One another algorithm to find the minimum spanning tree is Borukha's algorithm. The oldest and arguably simplest minimum spanning tree algorithm was discovered by the Czech mathematician Otakar Borukha in 1926, about a year after Jindřich Saxel asked him how to construct an electrical network connecting several cities using the least amount of wire. The algorithm was named after Gustav Shockway in 1938, rediscovered again by a team of Polish mathematicians led by Joseph Lukasiewicz in 1951 and rediscovered again by George Solin in 1961. Although Solin never published his rediscovery, it was carefully described and credited in one of the first textbooks on graph algorithms. As a result, this algorithm is sometimes called Solin's algorithm. In a similar way to Kruskal's, we join connected components of a forest at each iteration. Every component tracks the minimum cost edge, leaving it. At each iteration, we add these edges to the forest and update the tracked edges. It is easy to prove that the edges in each iteration must be acyclic between components. If there is a cycle, let the tracked cycle edges be E1, E2, so on up to Ek, where E1 has the minimum weight of the cycle. By choice of tracked edges, it must be that the weight of E1 is less than the weight of E2 and so on, such that the weight of Ek is less than the weight of E1, which is a contradiction. Let the number of components be k. At each step, Borukha's algorithm at least halves the number of components. In the worst case, there are k by 2 unique edges tracked and k by 2 components after joining. In the best case, there are k minus 1 unique edges and only one component remains after joining. Borukha's algorithm therefore runs in order of m log n time. Log n iterations check all the edges per iteration. The correctness for Borukha's algorithms are discussed in this theorem. The theorem states that for any cut S bar, the minimum weight edge in the cut must be in the minimum spanning tree. Assume for contradiction that in some cut S bar, the MST T does not choose the minimum weight edge E star. If we add E star to T, we get a cycle C. Obviously, some other edge of the tree also in the cycle crosses the cut. For all other edges E belonging to C intersection S bar, E not equal to E star, we have that the weight of E is greater than the weight of E star by our assumption on the uniqueness of weights. It follows that the tree formed by replacing any such E and with E star has strictly lower weight but remains spanning and connected. This contradicts our assumption that T was an MST, so for all cuts T must include the minimum weight edge. The next theorem is that for any cycle C in the graph, the maximum weight edge in C cannot be in any minimum spanning tree. Proof: consider any cycle C with the maximum weight edge E and assume for contradiction that E is in the minimum spanning tree T. Consider the cutoff T S, S bar is equal to E. Both sides of the cut are connected. Since there are no cycles in T, at least one other edge E dash belonging to C spans S bar and E dash does not belong to T. By choice of E, the weight of E is greater than the weight of E dash. Replacing E with E dash in T therefore gives a connected spanning tree with strictly lower cost, a contradiction to our choice of T. It follows that the maximum weight edge of any cycle is in no minimum spanning tree. So, we shall now see the Borovka's algorithm. For this graph, I am going to lead you step by step as to how to arrive at a minimum spanning tree. Now, write down the list of components. For this graph, we have A, B, C, D, E, F, G, H, I, J, K, L. So, these are the vertices and these are the edges, and each of these edges are having a weight. And the first step of Borovka's algorithm is to highlight the cheapest outgoing edge for every node in the list. So, for every node here, you need to choose the cheapest edge. So, from A to B and from A there are two edges going out. So, it is 1 and 7. The choice between 1 and 7 is quite obvious. You go for 1. Therefore, that is what we have chosen here, and we have shown this edge to be 1. So, from A the edge to be chosen is 1. Then we see B, there are 3 possibilities 2, 8 and 9. Again obvious, quite obvious, you have to choose the edge with the minimum, the cheapest weight, or the cheapest edge, or the edge with the minimum weight. So, this is why we choose B, C. So, and this edge is chosen, and that is why we have written it here. And next step is C. For the C, it is 1, 3, 2 possibilities, and out of 1 and 3 we need to choose 1 because that is the cheapest edge, and that is why you have highlighted C, H as the edge here. And you come to D. For D, there is only one way to go about it, because 3, 1, you cannot choose 3 because it will immediately create a cycle here. If you choose C, D, it will become a cycle and it might possibly create a cycle, but even then you have a 3 and 2, the choice between 3 and 2 is 2, quite obviously. So, 3 and 2, so 2 has been chosen, D and H, and therefore, we can never come back to this edge. Then, so we have chosen for A, B, C and D. Next we come to H. For H, there is 2 possibilities 6 and 5. So, 5 is the obvious choice. So, we choose 5. Then we come to G. G, there is 2 possibilities 5 and 9. So, obviously I go with 5. So, I draw this edge 5. Then finally, so G is covered, F is covered, then J. For J, there is only one way, so namely 3, that has been highlighted here. Then for K, there is 4 and there is 9. So, obviously I go with 4, that has been highlighted here. And finally, I come to E. E, there is only one way to do it. So, there is 4, and therefore, that has been highlighted. So, I have covered all the vertices. I have covered all the vertices in this graph, and I have highlighted the edge, that is the cheapest edge. For every single vertex, I have done this calculation. I have checked which is the cheapest edge, and I have highlighted. And the highlighting has been done in such a way that I have shown that there are 3 components while doing this, and it is a disconnected graph as of now. It is a disconnected graph. We still have not arrived at the minimum spanning tree. It is only a disconnected graph with this component highlighted in red. This is one component. The component highlighted in black is one component, and the component highlighted in blue is another component. So, 3 components. Among these 3 components, again I have to repeat the process in such a way that I choose the cheapest edge outside the component. This time for every single node, I have to choose the cheapest edge outside the component. But while doing this, you will be arriving at a lot of cycles and all that. So, the easiest way to do is to mentally calculate which component can be connected to which component by the cheapest edge. And therefore, I am going with let us look at this component. So, A, B, C, D, H, L, and this C and H have a cross edge, and this component can be connected with E or with this component, or it can be connected with this component. Using B and F you can draw a connection, or between G and H you can draw a connection. There are plenty of ways you can create the minimum spanning tree, but let me go with A first. So, if I go with A, I can connect it to E with a edge that is of weight 7, and or I can go with E and I can connect it with this component. So, E can be connected to this component using a edge that is of weight 4. So, obvious choice is I cannot go with this edge because it is of bigger weight than 7, bigger weight than 4, and therefore, I am going to go with this edge. So, let me draw that. So, I am choosing this edge. So, right now there is no longer 3 components, there is only 2 components. So, there is this component highlighted in red, and then there is this black and blue component, they have been fused together, and clearly there are no cycles involved. We have to avoid the cycles here. So, this I can stop here. Now, what about joining this component and this component? So, this is where I look at all the possible combinations. So, can I go from K to L? There is 6 here, there is a or I can go from G to H, there is a 6 here, or if I go from G to K, then there is a trouble because immediately here it forms a cycle. If I go from G to K, it forms a cycle here. So, I cannot go with G to K. So, out of all the possibilities, the cheapest way or the cheapest edge to be chosen is this, because here also it is 6 and here also it is 6. So, let me go with this edge. Therefore, I am choosing this. Now, you can very clearly see that it is now a complete a single component connected graph. It is a tree, clearly there are no cycles, it is connected. Therefore, we have arrived at the minimum spanning tree, because all the edges that we have chosen are obviously the minimum, and this is how you arrive at a minimum spanning tree using the Borovka's algorithm. Conclusion: in this section, we have seen about the minimum spanning tree algorithms. Specifically, we have discussed 2 algorithms, namely the Prim's algorithm and Borovka's algorithm, with examples and illustrations. And moreover, we have seen some of its characteristics. I hope you understood the algorithms. We will meet in the next session. Thank you.